This is the IRTF open meeting. If someone at the back could pull the doors in, please, that would be appreciated. All right, so thank you. Welcome, everybody. This is the IRTF open meeting. My name is Colin Perkins. I'm the IRTF chair. We have a bunch of things today. Quick introduction and status update to get us started. Then we have a short update from the Information-Centric Networking Research Group, talking about the CCNX RFCs. And then we'll spend the majority of the time today with two what look like really excellent talks from the Applied Networking Research Prize with Netta Rosen-Schiff sitting at the front here to start with, talking about NTP and a new NTP client called Kronos, and TJ Chung at the end talking about the role of registrars in DNSSEC deployment. A really nice measurement study there. It's a lot of echo. Closer or further? Closer. Is this better? Yes. Okay, excellent. All right. It's even more echoey from where I'm sitting, but if it's better for you, that's good. Okay, so this is the IRTF open meeting. The IRTF, as a reminder, is a parallel organization to the IETF, which focuses on the longer-term research issues. We've got a bunch of mailing lists, which you may consider joining. We've got an announcements list, which is pretty low volume, and a discussion list. And we have the IRTF.org website, which has all the information about the organization. We do three types of things in the IRTF. We've got a bunch of research groups, of which there are 11 full research groups and 3 proposed research groups. We cover a pretty full range of the possible subjects, from the crypto forum group all the way through to quantum internet, network measurement, information-centric networking, human rights, global access, and so on. The groups in dark green are full research groups. The ones in light green and gray are proposed research groups. We let new research groups run for a year, see if things are working, and if so, they then get chartered as a full research group. The COIN group had its first meeting in Prague, the Computation in the Network group. They look to be doing some really nice stuff on in-network computing. The Privacy Enhancements group will be having their third meeting later this week, and I expect they'll transition to a full research group shortly after that. And the Quantum Internet group, who are not meeting this time, had a really nice tutorial in Prague, which I understood not a word of, about quantum internet and the quantum physics, the physics behind what it needs to build a quantum link. And look to be doing some really nice work. They're alternating their meetings between here and quantum physics conferences, so they're not meeting this time. We also have the Applied Networking Research Workshop, which ran yesterday. We had a couple of hundred people in attendance, a bunch of really nice papers. This is a conference we organize in conjunction with ACM SIGCOM. Proceedings are published in the ACM Digital Library. It's a peer-reviewed workshop. We've got some really nice papers, which are all on the website. We hope to do this all again next year. Still a little bit provisional, but hopefully this will be running again in the summer IETF in Madrid next year. So look out for the call for papers around Christmas time, just after. And finally, we have the Applied Networking Research Prize, which is awarded for some results in recent results in applied networking research. And we'll have the 2 talks, which will comprise the majority of this session. Talking about NTP security and talking about DNSSEC deployment. There'll be a couple more ANRP talks at IETF 106 in Singapore, and we'll be opening nominations for the 2020 awards come October, November time. So if you've read any good applied networking research papers, keep them in mind. We'd appreciate your nominations later in the year. Okay. So that's all I have to say. Before we move on to the ANRP talks, we just have a short talk, if I can find it, on CCNX. And it's gone. Find this.
All right, thank you. So my name is, while he's pulling them up, my name is Mark Moscow. I'm the principal author on the two experimental specs that just got released for CCNX from the ICNRG.
Keep talking. Can't work the Chromebook.
Okay, there we go. So there were two documents released as part of this protocol. The first is the 8569, the semantics document, which describes the behavior and the meaning of the different fields. And then there's an encoding document, 8609, which uses a mostly TLV format to encode the protocol messages. So for those of you who don't know, CCNX is one of the ICNRG information-centric networking protocols, and the idea here is that you do something to name the data that you're requesting, and you can use that name in fetching the data, so you're not doing quite host-to-host networking. You're trying to get something by its content. This was first proposed in 2009 and went under a significant revision beginning in 2014. The first drafts, I think, were submitted in 2016. So it's been kind of a long march for these specifications. And just to give you one of the high-level use cases, it's an interest and request-response protocol. So I can ask for some name like example.com/photo.manifest, and I can specify the key that the publisher used to publish this, and the network can ensure that I get I get the data that I asked for, and then we can do tricks with how to fetch data by hash-based naming once you have a manifest for that data. There are 4 principal implementations that are going right now. One is called Community ICN, and this is the Linux Foundation work, and this is meant to be a fairly high-speed implementation that uses vector packet processing. CCN Lite, which is a widely used implementation, especially on smaller platforms. And C4, this is from the National Research Institute of Japan, and this has also simulator and emulator modules available for it. So all of these are based on the CCNX RFCs. Hybrid ICN looks at integrating name-based routing into the IPv6 address space, so between the IPv6 address and the transport address, it's kind of fully integrates. So it's not really an overlay, it's an integration. So thank you very much.
Okay, thank you. We maybe have time for one quick question if anyone has one. It's a nice piece of work just finishing up from the ICN group.
Thank you.
Okay, thank you. Netta, you're up. Okay. Clicker as well. Okay, so the first of the 2 Applied Networking Research Prize winning talks is Netta Rosenschiff from the Hebrew University in Jerusalem, who will be talking about preventing network time travel with Kronos. Go.
Yeah. Okay. Hi, I'm Neta, and today I'm going to present a work on how to protect NTP with the Honus. It's a joint work with Omer Deutsch, Danny Dolev, and Michal Shapira. So NTP, Network Line Protocol, it is used to synchronize time across the computer over the internet. I guess you all know how measured this protocol is. Many applications rely on it, such as TLS, DNS, HTTPS, Kerberos, and many financial applications. In a nutshell, NTP is a client-server architecture, consists of two main processes, poll process and selection process. So, for example, if we have one client that in the poll process sends NTP queries to 3 NTP servers, gets NTP responses from the NTP servers, and then in the selection process, the best time samples are selected and used in order to update the client clock. However, NTP is highly vulnerable to time-shifting attacks, especially made by man-in-the-middle attacker who have a control over the section between a client and one of the NTP servers. And for example, in the previous one, let's assume without all loss of generality that the man in the middle control the section between the client and the left NTP server. Man in the middle attacker can tamper NTP responses. He can impact the local clock of the client by simply dropping or delaying packets. That is why encryption and authentication are insufficient here. And he can make the client believe that his sample is the best one and he should follow. Previous studies even consider man in the middle as too strong for NTP. But why is NTP so vulnerable to man in the middle anyway? As we said before, NTP consists of two main processes, poll process and selection process. In the poll process, the NTP relies on a very small set of servers, and they are often DNS cached, which means that the attacker only needs man-in-the-middle capabilities with respect of few NTP servers in order to maintain his attack over time. And the NTP selection process algorithms assume that incurrency are rare and they are well distributed around the UTC, the correct time. That is why powerful and sophisticated man-in-the-middle attacker can bypass this algorithm, and he's beyond the scope of traditional threat models. In order to face these limitations, we suggest a modified NTP client called Honus. It has the following characteristics. It has provable security. We can bound the probability of successful time-shifting attacks, even made by man-in-the-middle attacker. We can, it's backward compatibility since there is no need to change anything in the server side, only small and limited changes are needed in the client side. And we add only low computational and communicational overhead since eventually we query only few NTP servers. So in order to prove that Honus actually protect NTP, we need to define our threat model. So we assume that the attacker have full control over a large function of the NTP servers, say quarter. We also assume that he is capable of both modifying the content of the NTP response and the timing when it's going to arrive to the client. And finally, we assume that he is malicious and try to shift the client's clock as much as possible. So how Honus is built? On the one hand, we rely on many NTP servers. We generate a large server pool, 100 of servers per client, in order to raise the threshold needed by the attacker to attack. On the other hand, we query only few servers. Only tens of them are choosing at random in order to avoid NTP overloading, NTP servers overloading. And finally, we use smart filtering in order to remove outliers and make it hard to the man-in-the-middle attacker to contaminate the chosen samples. So now out of the pool, I'm informally going to describe how we update our clock. So out of 100 of servers in the pool, we choose tens of them at random. Then we order them from low to high. We remove the D lowest and the D highest time samples and take a look at the remaining set. And then we ask two questions. We have two conditions. The first one is whether the samples in the remaining set are close to each other, And the other condition is whether their average is close to the client's clock. If both of these conditions are satisfied, then we use the average of the remaining set as the new client's clock. Otherwise, we resample. And again, out of hundreds of servers, tenants are chosen at random. We drop D from each side. D could be, for example, 1/3. And we take a look at the remaining set and test the two conditions, whether they're close to each other and whether their average is close to the client's clock. If we fail, we try again and again and again and again until we fail k times. And then we move to the panic mode, where we sample all the servers, dropped D, for example, 1/3 from each side, and take the new time of the client as the average. So first I'm going to present our security guarantees, and then I will describe our security analysis. So essentially, what we are showing in our paper is that shifting time at one client by at least 100 milliseconds from the UTC will take the attacker at least 22 years in expectation. And this is when we consider an extreme case where out of 500 servers in the pool, 7 of whom are fully controlled by the attacker. We also query 15 servers per hour, and we saw that good samples are within 25 milliseconds from the UTC. We call this parameter omega. These parameters are derived from experiments that we conducted on Amazon servers, both in Europe and in the US. And here you can see the benefit of using Chronos over the current NTP as a function of the x-axis, the number of servers that are queried per update, where each line here presents a different ratio of the malicious server in the pool. So consider a pool of 500 servers, a P function of which are fully controlled by the attacker, and now we compute the attacker probability of success for time-shifting attack, both in the traditional NTP client and in Chronos NTP client. We plot the ratio between these probabilities, and this is the y-axis. So if we consider the last scenario, when we have out of 500 servers, 7 of whom are fully controlled by the attacker, we can see that using Chronos improve the security by a factor of 1,000. Notice that the y-axis is logarithmic, and that's why the improvement is exponential. And now we are going to describe our security analysis. So in order to do so, we have to look at all the scenarios that can happen, which depends on the number of malicious samples that we queried, and see how Chronos is handling them. Of course, we take the worst scenario in every case. The worst case in every scenario. And the first scenario is when the number of good samples is D. As you remember, out of 100 of servers, we chose M, 10s at random, and then we dropped D from each side. So in the first scenario, we have the number of good samples, denoted as yellow angel, is higher than D, and then the number of malicious samples, denoted as red diamond, is less than M minus D. So we have two options here, because the first one is when we have only a malicious sample remaining in our remaining set. However, we have more than D good samples, right? So we have at least one good sample in each side of the remaining set, which means, and good samples are within omega away from the UTC, from the correct time. That is why the remaining set samples should be also close to the UTC. And their average that we use in order to update our clock eventually is close to the UTC. The second option is when we have at least one good sample inside our remaining set. However, according to our first condition, all the samples in the remaining set should be close to each other, otherwise we resample. So if we know that we have at least one good sample in the remaining set, and it's close to the UTC, the others should be close to it, which means that their average also will be close to the UTC. And this is why we can say that these attack strategies are ineffective. The second scenario is when the number of good samples is equal or less than D, and the number of malicious servers is higher or equal to A minus D. In the worst case, we have only malicious servers remaining, and they are not bounded by good samples. However, according to our second condition, their average, which we finally use in order to update our clock, should be close to the client's clock, which means that there is a boundary on the time shift that we allow here. Moreover, the probability of this kind of scenario is extremely low. Why? Because it requires the malicious samples to be randomly chosen in much higher rate than the rate in the population. And of course, repeated shifts probability is negligible. This is why we can say that significant time shift here is practically infeasible. But even if we cannot really shift the client's clock, maybe we can create another kind of attack, let's say denial of service. So how can we do that? If we have more than D malicious servers and less than A minus D good servers, good samples, sorry, then we have at least one malicious sample that remain in our remaining set, right? So it can violate, for example, the first condition saying that all the samples should be close to each other, and then cause us to resample. Resampling again and again and again, we get to the panic mode when we ask all the servers in the pool. And maybe multiple resampling by multiple clients, Kronos client, may cause denial of service over the NTP servers. However, we can prove that even for low panic threshold, k equals 3 means that only after 3 failures you move to the panic mode and ask all the servers in the pool, the probability of success is negligible, which means that it will take the attacker decades to force panic mode on one server, on one Kronos client, sorry. And when we compare between Kronos and NTPD, we see that Kronos using a greater variety of sampled server over time. It has provable security guarantees, as I presented, and it avoids the NTP source quality filters. This is why it is possible that there is an adverse effect on its precision and occurrency. So in order to improve the precision, without, of course, sacrificing Kronos security, we introduce a smoothing mechanism that's saying that we favor the minimal sample offset out of all the offsets in the remaining set if it's close to the average offset. We evaluate Kronos with the smoothing mechanism in multiple locations, both in Europe and in the US. For example, this is the result from Oregon, where you can see in the x-axis is the average offset, and in the y-axis is the fluctuation, the average offset derivative. Each dot here represents 30 minutes experiment that conduct in each of these algorithms. And we compare NTP in blue dot to Kronos with the smoothing mechanism in the red dots. And we can see here that essentially the average offsets are close to each other, both in NTP and in Kronos, and there is not much fluctuation in both of them. So to conclude, NTP is highly vulnerable to time shifting attacks, and even attacker who controls even fewer sections between servers and client can shift the client's time. So we presented a modified NTP client called Kronos with provable security, backward compatibility, and low overhead. And we also showed that Kronos precision and offsets are very close to the NTP, around 2 milliseconds apart. And this is the research, the further research. So we continue to evaluate Kronos at scale, security, precision, accuracy, overhead, etc. We also working on standardized HONUS in the relevant working group, and we would like to extend HONUS to address several attack strategies. And of course, we would like to extend HONUS to maybe other time synchronization protocols such as PTP. And here you can see that the link to both our paper published in NDSS and our last IETF draft. Thank you very much, and I can take questions now.
Okay, thank you. Okay, are there any questions?
Hi, I'm Stuart Cheshire from Apple. This is important work, thank you. I have a little tip. If you put numbers on the slides, it makes it easier to ask questions. So I don't know what the slide number was, but earlier in the presentation you had a graph showing how the probability improves as the sample size improves, which makes perfect sense. But it was kind of a staircase shape, and I was puzzled. What is the intuition why it's not a monotonic increase in security as the sample size goes up?
Yeah, you refer to this, to this graph. Yeah,
it seems like going from 14 to 18, it gets worse, and then it improves at 20.
Not, okay, this is just a stimulation effect, but basically we are, because the current NTP uses between 4 and 6 servers, we didn't really calculate before. And so this is the answer about why it is getting worse. And why it's a straight line and not really increasing, the answer is that we would like to remove D from each side. D was 1/3, and we wanted it to be an integer number, so this is why you can see the stairs.
So is the conclusion that querying 8 servers actually gives you better results than querying 12?
No, it's not. It's not that, no, it's kind of straight line. But
I see. I think it's an optical illusion. So those lines are horizontal, are they? It actually looks like it's sloping down. Okay.
Yeah, it's a straight line.
So it's a flat plateau. I get it now. Okay.
Yeah,
thanks.
it is. Yeah. And what we can see here is that even if we are sample only 10 servers are current over time, then still HONUS improve the current NTP by a factor of 100.
Hi, Wes Herdeker, ISI. Good work. I love seeing a good statistical analysis of your security likelihood. I think that's great. And it looks like it's a feasible solution with one exception. So I assume it sounds like you don't try and handle man-in-the-middle type attacks where you have an attacker very close to you that can almost respond to most NTP servers, right? So that, okay, thank you.
Yeah, exactly. If it's like if he controlled my gateway, for example. So yeah, it's a game over. Yeah.
Hello, Alexandre Ferrieux from Orange. It seems like your last validation step is to compare to the current clock, right?
Yeah, yes. I compared HONUS to the current NTP.
Okay,
yeah.
So if a significant number of machines in a pool get a huge drift, they will all switch to panic mode as soon as they are switched back on, right?
You're talking about the current NTP or HONUS? If you're saying that if all
yeah, for example, imagine a bunch of machines that you just remove from the network from some time, and their clocks drift.
Yeah.
And then back, you connect them back to the internet.
Yeah, I have a drift, that's right.
Okay, so they all get to panic mode.
Yes, in our draft, we are saying that in a startup, for now we use a panic mode as a startup mode, but we are working on it, and maybe we can, we don't have to really query all the servers, but only maybe a factor of 2 of the servers that we already query at random, maybe 2M, for example, in order to get to the same results. So this is exactly what we're working on. Thank you.
Hello there. I looked for the answer in your paper, but unfortunately the link at the end of your presentation doesn't work. So I'm going to look for your paper somewhere else. But just so you know, the link
okay.
doesn't work.
Okay, so I will fix it and I will send you the presentation, so it will be on the web. Great,
Super.
thank you.
My question is there a general result here with regards to security and the digestion of untrusted sources that you're based on?
Yeah, I think that the bottom line is that we can use a crowdsourcing in order to maybe use and use, for instance, Honus as a watchdog to NTP, and see if there is a huge shift, then maybe we can move to more secure mechanism. Yeah.
Okay, thanks.
There is a working link to the paper from the IRTF.org site.
Hi, Anshul Malhotra from Boston University. Did you do any analysis on the current NTP client with fixed? So current NTP client has a fixed number of servers, right? That it queries. It has a fixed number of servers. So with the fixed number of servers and using your modified algorithm, does it provide the similar guarantees, or is it similar security guarantees? If this client is querying a fixed number of servers as opposed to randomly selecting from a large pool and using your modified algorithm for selection, does it give the similar security guarantees? Or
if I fix the servers in advance and then just drop the from each side, this is what you're asking?
Yes, yes.
So the problem is that when I do that, so once I have a malicious sample in my remaining set, it will continue to be in my remaining set, or it will continuously be in the. I continue to ask the same server again and again and again. And if he is malicious, if he's under the control of malicious attacker, then he can do the repeated shift time. I mean, I allow it to do a very limited time shift. And the fact that I'm telling that repeated time shift is probability is negligible is because I'm querying different servers all the time. Otherwise, I won't be able to say that.
Okay, so, all right, thanks.
Okay, any more questions? No? Did you talk to the NTP working group while you're here?
Yeah, the chair is sitting
Yeah,
right here.
He's right here. Okay,
Yeah,
excellent.
And we wrote several draft, and I hope it will be adopted as a working group draft. And yeah.
Okay, I'm glad to hear it. Okay, thank you very much.
Thank you.
Okay, we'll give it a try. Not working.
It's weird because when I tested, it worked.
No, it's not working on the video.
Oh, I need an animation.
We have to go back to here. Okay, hang on. Just one second. Hang on. Can't work Chromebook either.
I'm sorry, guys.
It really does, yeah. These are supposedly user-friendly.
I worry about that if I lost my prize. But
So 100%. Try full screen now. No, that's not working. Yes, all right, there we go. Is it working? No. Maybe this is going to work. All right, so the second talk is TJ Chung from Register Institute of Tech, who will be talking about DNSSEC deployment.
thanks for the introduction, Colin. Hi, my name is TJ from IRT, assistant professor. First of all, I'm very excited to talk about research, and actually this is my first IETF, and I'm really excited to see how smart is the people making a decision by humming. So this talk is about DNS and DNSSEC. So inevitably, I need to give you some introduction of how DNS and DNSSEC works. I'm a little bit scared to talk about the introduction of DNS in front of you, actually making a standard internet, but let me try my best. So DNS is like yellow pages in the internet. It translates a human readable name to machine readable name, such as IP address. So I'm sorry, there should be a animation, but it was missing. So when you send the DNS request from your host, when you type a domain name on your browser is configured to use your local resolvers, and the DNS resolver will send the DNS request to the authoritative DNS servers, and the server will return the response to the resolver and forward it back to the browser so that you can see the content, right? But unfortunately, the syncing is not good, but browser, the DNS message is just plain text, so the bad guy in the middle of the path can snatch the packet and insert the wrong IP address to make you see the different content, such as advertisement. So to prevent from this attack, DNSSEC was introduced about 20 years ago. The idea is very simple. Let's deploy public and private key infrastructure on the DNS side. So example.com now manages a key pair, private and public key pairs, and when the DNS request comes, it responds with the signature. So to verify the signatures, the resolver also need to have a public key part. So the public key is in the DNS key record. So here is another problem, how the resolver guarantee that this public key actually belongs to the example.com. So DNSSEC mirrors existing hierarchy of DNS. So now .com zone also have DNS key, public key and private key, and use this key to sign example.com's DNS key. And of course, .com zone's DNS key is also signed by root DNS key. Then how does the resolver verify the DNS root key? It is prefetched. So as you can tell, there is a chain of trust. Root signs .com signs example.com, and example.com signs DNS record, right? So let's see how this actual chain of trust, making a chain of trust process works. Because making a chain of trust between root and .com and example.com are basically same. So let's focus on the later one. So the key concept is very simple. So if you're the owner of example.com, and if you want to make a chain of trust, then what you need to do is first generate a DS record. So DS record is just a hash of your DNS key, so it is basically a long string, long hashed string. After that, you have to upload it to your parent zone. So in this case, .com zone. Then .com zone will sign this DNS key record, and I'm sorry for the animation, and also it generates a signature. So when a resolver wants to verify if this DNS key is valid, it has to fetch a DS record from the parent zone. is challenging, yes. DNSSEC is challenging, right? So it was introduced about 20 years ago, but still not working, right? All right, so, yeah. You have a eagle eye, right? All right, here we go. Yeah. Yeah, yes. Yeah, so if a reserver fetches a DS record from the parent zone and fetch a DNS key from the child zone, if it is the same, then it's done. Of course, you need to verify the signature of the DS record signed by .com zone, of course. So if you're the owner of a domain name, if you want to deploy DNSSEC, you need to follow these 3 steps. First, you need to have a DNS key, and using this key, you have to generate a signature. At the last step, you have to generate a DS record and upload it to your parent zone. So the question and answer for this research, this analysis is how many domains out there follow these steps. So to do that, we used OpenIntel dataset, which collects all the domain names under .com, .org, .net, almost 2 years. So let's see. Actually, there was a black box to hide the graph to make you see to make you surprised, but it is already revealed. Surprisingly, we found that only 1% of domains deployed DNS key, even though it was introduced about 20 years ago. So, but the good part is it's growing, right? So, okay. Then how about the signatures? So y-axis shows % of domains missing signature.
Keep talking. we can see it in the middle, so keep talking.
Okay. So, yep. So y-axis shows % of missing signatures. So as you can tell, nearly 0.2% of domain names with DNS key miss the signature. So signatures are rarely missing. There is a huge drop at this point. This is due to one registrar. I don't want to call a name, but they used to have a DNS key. They equipped with DNS key, but for some reason, they forgot to sign it. But after that point, they finally generated signatures, so that is the reason why there's a huge drop. Then how about the final one? The last piece of puzzle is you need to generate a DS record and upload it to the parent zone. So y-axis is % of domains missing DS record. Surprisingly, we found that nearly 30% of domains do not upload a DS record. So as you can tell, there are 2 problems here. First one is, why does the DNSSEC deployment remain so small even though it was introduced about 20 years ago? And the second problem is, why are 30% of domains still without a DS record? Now, why the screen is not working? So there are 2 main questions for this talk. The first one is, why is it so hard to deploy DNSSEC? And as you can tell from the title of this talk, how does a registrar policy impact on the deployment? So let's first focus on the first one. So to understand that, you have to understand how you can purchase your domain name and how to deploy DNSSEC. So let's say if you want to buy a domain name, you typically go to a registrar, for example, GoDaddy. So a registrar is an organization that sells a domain name to the public, and also it has access to the database managed by Registry. So Registry is basically top-level domain name zone. For example, .com is managed by VeriSign. And after that, after purchasing a domain name, you also need to have a name servers. So first choice you can make is you can just use a name server provided by the registrar. So in this case, if you want to deploy a DNSSEC, then GoDaddy will generate a DNS key, signatures, and also DS record, right? And also, it has an access to the database managed by Registry, so that it can simply, easily upload a DS record to the Registry, right? The second choice is you can run your own name server. You bought a host, and after that, install a bind or DNSSEC software, generate signatures as well as DS record, but here, you do not have any access to the registry. So what you need to do is to generate a DS record and give it to the registrar and ask them to upload it to the registry. Let's say you're using third-party DNS operator. So in this case, for example, Cloudflare will manage all the DNSSEC records for you, including generating signatures, DS record. But again, third-party DNS operator doesn't have any access to the registry, so you need to copy the string DS record, which is basically a long string, copy it, and pass it to the registrar, and ask them to upload it to the registry. If you think this process is complex, actually I can make it even worse. So for example, let's say you bought a domain name from a reseller. Reseller is an organization that sells a domain name to the public, but it doesn't have any authority to contact to the registry. So what they do is to partner with a registrar. So if you purchase a domain name from a reseller and are using a third-party DNS operator, then you need to copy a DS record and pass it to the reseller and ask them to upload it to the registrar and registry. Such a simple process. What could it possibly go wrong? So, as you can tell, the key part of deploying DNSSEC is registrar. So what I'm going to do is, what I'm going to show you is, showing the result that we surveyed by surveying popular registrar with lots of domain name. So what we do is, we first purchase a domain name from a registrar, and we see if they simply support DNSSEC on their name servers. After that, we disable it, we run our own name servers, generate a DS record, and ask them if you guys can upload a DS record to the registry. If they do, we deliberately give them an incorrect DS record, which is not matched with DNS key. The reason is that because if the registrar does not check the validity of the DNS key and the DS record and simply upload it to the registry, then your domain name will be instantly inaccessible to the reserver that support DNSSEC, such as Google Reserver or Cloudflare Reserver. So before showing this, before showing all the details of the analysis, I'm going to give you some anecdotal examples that we experienced during our experiment. The first one is, we saw the DNS key deployed for one registrar, but not DS record. So ask why you guys do not upload the DS record. The first response was that, oh, they removed the DNSSEC menu. And another registrar responded back to me saying that, hey, most people do not understand DNS, so imagine their white faces when I'm mentioning DNSSEC. So yeah, this is what happened. And also, we asked a registrar to upload a DS record by email from the different email address than the one we used to register. It was installed successfully. And also, we asked a registrar to upload a DS record to our domain name, a domain via web live chat. It was installed successfully to someone else's domain name due to a mistake by customer agent. Yeah, usually the customer agent, opens a multiple tab to deal with multiple customers, so just made a mistake to paste the DS record to the other domain name. So this is the detail. Hey, I'd like to update my DS record. So awesome, one moment. So I now update your DS record to pananamusic.com, right? I'm sorry, but my domain is hgdnssec.com. Oh, I apologize, you're silly me. Yep. You're right, silly me. So one moment. So after I got this response, I tried to connect to pananamusic.com using my, using Google reservers, but the response was server failure. Yep. So This is the survey result that we surveyed about 20 registrar that takes about 50% or nearly 50% of all domain names of .com, .org, .net. Sadly, only 4 registrars support DNSSEC on their name servers, which is not good. For your information, we redone, actually this study was done about 2017, but for this talk, we just redid all the survey a few weeks ago. And after that, we disable we run our own name servers and disable the default name server provided by Registrar, and we asked them to upload a DS record. Interestingly, 15 out of 20 registrars support a DS record upload. So mainly there are 2 functionalities. So first one is, for example, web supporting ticket or web live chat. So using this methodology, they allows us to upload the DS record. Or some registrars ask us to send the email with the content is, of course, the long string of a DS record. And sadly, only 5 out of 20 check the verification. So yeah, if you happen to deliver a incorrect DS record, your domain name will be instantly inaccessible to the DNSSEC supporting reservers. So here's the summary. Only 4 out of 20 support, 4 out of 20 registrars support DNSSEC on their name servers. What this means to you is, if you don't want to run your own name server most of the time, you cannot deploy DNSSEC. If you want to run your own name servers, still, you cannot deploy DNSSEC for 5 out of 20. And only 5 registrars support, check the DS record verification, which means if you happen to upload an incorrect DS record due to copy and paste error, then your domain name will be inaccessible, right? Then the next question is, why are this DNSSEC support of registrars so rare? Why is that? Actually, we already know the answer. Because DNSSEC introduced much more records, right? Because basically it needs signatures for every DNS records, and also signatures are usually 3 to 6 times larger than non-DNSSEC records. And also DNS keys, like your password, you have to choose strong key, and also unique key, and also you have to roll over the key regular basis. Actually, you already seen how this policy impact on DNSSEC deployment. For example, we saw that 4 out of 20 registrars support DNSSEC on their name servers, but interestingly, 15 out of 20 allow us to upload a DS record, right? The thing is, in the first case, when the registrars run the name server with DNSSEC, they need to manage all DNS records, right, in their name servers. But if the owner wants to run their own name servers, then what the registrar needs to do is to simply receive a DS record and upload it to the registry. Done. They don't need to manage all the DNS records at all. So let's compare the 2017 result. So our study was done in 2017 March. So at the time, only 3 out of 20 registrars supported the DNSSEC on their name servers, at the registrar side name servers, and 11 out of 20 supporting it when the users want to use their own name servers, and 2 out of them check the verification. So as you can tell, it has been improved, but yep, it has been improved. It's much better than decreasing, something like that, but still way to go. So now let's switch gear to how does the registrar policy impact the deployment. To see that, we also use the historical data set. So to see that, we first focus on the .com, .org, .net data set, but as you already seen, the deployment ratio is very small, less than 1%. But we happen to know that .nl, .sc, this 2 system TLD's DNSSEC deployment ratio is nearly 50%, which is really good. And also we updated our data set by considering the most recent data set, 2019. Actually, the percent with DNS key field is hidden due to the animation fault, but it was increased by 0.1%. So, yeah, but still increased. So, So let's see how a registrar policy impact on DNSSEC deployment. In other words, how can we encourage a registrar to support DNSSEC? The first perspective is registry. So we happen to notice that the KPN Dutch registrar and Lupia Swedish registrar gain a financial incentive from the registry when they activate DNSSEC for the domain names they manage. So as you can tell, .nl, .se, these two domain names, DNSSEC deployment ratio is nearly 90%, which is awesome. But how about the other three domain names, .org, .net, .com, where they cannot get any financial incentive? So as you can tell, actually, I already drew the figure line here. It's nearly 0%. So which means financial gain is a huge incentive for deploying DNSSEC. They only deploy DNSSEC when they can get a financial incentive. The second perspective is registrar. So we found that OVH and GoDaddy, two registrars supporting DNSSEC on their default name servers. But OVH provides it for free, but GoDaddy you have to obtain by paying $35 per year to activate DNSSEC. As you can expect, the OVH DNSSEC deployment ratio is over 20%, but GoDaddy is nearly 0%. So free DNSSEC, of course, support encourages user to deploy DNSSEC. And the third perspective is reseller. One registrar called Antagonist is a registrar for NL domain name, but they're a reseller for .com, .org, .net. So the top graph shows the number of domains they manage, and the bottom graph shows the percent of domains with the DNS key and the DS record. So as you can tell from the white line, the DNSSEC deployment ratio for NL is nearly 100%, which is good. But interestingly, we observed that there is a gradual deployment increasing ratio for the other domain names. The reason is that this registrar, this Antagonist, actually started to deploy DNSSEC at the end of 2014. But what happened was they switched a registrar that's supporting a DNSSEC. But the migration only happens when the current domain name expires. So after the previous domain name expires, they migrate to a new registrar that supports DNSSEC. So that is the reason why you can see kind of gradual deployment. So complex relationship between reseller and registrar also result in a kind of slow deployment of DNSSEC. And the other perspective is third-party DNS operator. So for your recall, if you're using a third-party DNS operator, if you want to use DNSSEC, then you have to copy a DS record from a third-party DNS operator and pass it to your registrar and ask them to upload it to the registry. So Cloudflare actually announced the universal DNSSEC in 2016, early 2016. So if you want to use Cloudflare's DNSSEC, you have to opt in, and Cloudflare DNS server will generate a DNS key, signature, as well as DS record. So what you need to do is copy this DS record and pass it to the registrar to ask them to upload it to the registry. But the top graph shows percent of DNS key with DS record. But interestingly, even though the DNS key deployment in the bottom graph increasing, right? But still, 50% of domain names with DNS key still failing to deploy a DS record. This could be either one, the administrators did not understand correctly how to deploy DNSSEC correctly, or their registrar does not simply allow the users to upload a DS record. So deploying DNSSEC is even harder for users using third-party DNS operator. So here's the conclusion. So registrars play a critical role in supporting DNSSEC today. Only 4 out of 20 registrars support DNSSEC under authoritative name servers. But interestingly, 15 out of 20 support uploading a custom DS record. So comparing to the result of 2017, it has been improved, but it requires much more effort. So DNSSEC deployment depends on many policies. Registrar should support it for free. Registry, it would be great if they can offer financial incentive. And reseller, be aware to choose a partner registrar. And also, when you're using third party, I guess the CDNS key new protocol, which allow users to upload a DS record directly to the registry without any support from the registrar. This will be a very good solution, I guess. So that's it, and thanks for your attention, and I'm happy to take any questions.
Okay, thank you. All right, that was an excellent talk in some very difficult circumstances with the projector. Does anyone have any questions?
Wes Herdeker, ISI, great talk. Entertaining too. And I don't mean because of the projector blinking. Are you continuing to do long-running statistics gathering, and are you publishing it live at all? And then I might offer to collaborate a little bit. So I actually have a web page called stats.dnssec-tools.org where we and Victor Duchovny publish continually daily updating stats of DNSSEC deployment and Dane deployment in particular. And it would be really cool to merge those because I think Victor has a lot of data that you probably don't have, and you have a lot of data that I think Victor doesn't have, so we should talk.
Yep, sure, absolutely.
But are you running it continually, or are you?
Yep.
Okay, awesome.
Hi, nice talk. This is Pallavi, RS from Salesforce. So one of the angle to this whole research could be, and I'm speaking from experience, is that when the client is big, like if your domain name is used by a lot of customers, you try to make the domain name multi-vendor, so you might have your zone hosted on maybe Cloudflare and one more provider. So your zone might be xyz.com or whatever, might be multi-vendor where it's hosted on provider 1 and provider 2. In that case, again, achieving DNSSEC is hard because just matching the keys and DS records. So that's another angle that you can look at of the zones that you're scanning. If they are multi-vendor, in that case also they may not be, it's not easy to do DNS signing and all that. So we actually have a draft in DNS Ops related to this, but we'll be happy to talk to you about it.
Yeah, actually I'm not familiar with that area, but I'm happy to take a look. Yeah, thanks.
All right, Paula Brisbane from Newstar. Nice presentation. You might also, on those 30% that don't have DS records, one of the very common things that happens is people start playing with DNSSEC, and the first thing they do when they aren't sure is they'll yank the DS records from the parent, because then you simply go undetermined as opposed to going invalid. So you may want to start going back and resampling on a recurring basis of who may have DS records appearing and disappearing.
Yep.
It's also one of the vectors that people are using with hijacking is that the first thing they will do is they will change and remove the DS records and change the DNS in the parent and start playing games.
Thanks.
Can I respond to that as well? I was one of the co-authors of this paper. We looked at that, and it's not people playing around with DNSSEC. It's people simply not deploying a DS in one TLD. They sign everything they own. They sign their whole portfolio. But then they only deploy a DS in the TLDs that give them a financial incentive, such as .nl and .sc. There are some positive side effects because there are people that sign everything because of the financial incentive, but then also deploy the DS in every TLD, which is what people should have been doing. There are some positive side effects from other incentives that TLDs are now deploying, for example, for the deployment of Dane, TLSA records, where you see as a side effect also an uptake of DNSSEC Day in other TLDs than the ones that deploy the incentive. So I'd like to applaud Ulrich, who's over there, for .cc for deploying that incentive as well.
Thanks, Roland.
Hi, I'm Ulrich from the Swedish Internet Foundation. We do run .se. So I just want to say very nice work. The only critic I have is that you didn't test our registrars. So
I'm sorry, didn't test where?
You didn't test our registrars. We would like to have this test on our registrars because it's, we want to promote DNSSEC. And
Yep.
so very good work, and we will look into it. Thank you.
Thanks so much.
Rick Wilhelm, VeriSign. Just one question in chart 24, one good presentation, certainly appreciated. On chart 24, this is where sort of the 15 out of
Let me see, 24.
Different chart 24. This is where the chart where the 15 out of 20 comes up. And I'm curious as to why the ones that provide the upload via email, yeah, this one here, why they weren't counted as being supportive of DNSSEC, even though they don't appear to do it based on when the research was done through their web portal. Those registrars you indicate here do support DNSSEC.
I'm sorry, can you repeat the question?
Sure,
First
sorry.
one? Yeah, I'm sorry.
Okay, so on this chart, this is where the number 15 out of 20 comes from,
Yep.
the ones that support. And
Yep.
I'm curious as to why the ones in the lower right corner, those there weren't included in the count as supporting DNSSEC.
Yeah, included.
Oh, they are. Okay. Okay, my bad. So the other 5, but you don't name the other 5 registrars.
The others, the bottom
Okay.
row, 5 registered, did not support DNSSEC.
They don't do anything.
Yep,
okay.
no.
And then the only other thing I would offer is that in the at least in the COM registry, there's a very large number, as Ulrich notes, lots of registrars participate, and with varying levels of participation for both allowing DNSSEC through their
Nice.
portal and also with the other names.
Yep.
Thanks.
Sweet.
Okay. Any more? One more.
Jody Kalker from GoDaddy. I'm just curious, do you have any data on maybe the top 100,000 Alexa websites that are using DNSSEC?
Yes, we do, but not for this paper. Actually, we published the one on another paper at the Using Security 2017. There is a research for the Alexa 1 million website if the ratio of the domain names supporting DNSSEC, but it's very low. It's less than 2%, I guess.
So why do you think that some of the largest retailers don't use DNSSEC? They are the most vulnerable for this, aren't they?
I'm sorry, can you repeat it?
Sure. Why do the largest retailers on the internet?
Largest?
Retailers.
Retailers.
Businesses.
You mean the registrar?
No, the people that make
Yep.
the money off the internet, like Amazon. Why do they not use DNSSEC? If anyone's from Amazon is here, I'd love to hear the answer. Google?
If I were to be a Sergey, then I could answer. But I'm sorry, I have no idea. They should supporting it, but
Well, I think what the issue is here is that as many domains that you're looking at, most of them are for small to medium businesses.
Mhm.
Small to medium businesses don't have an IT department.
Mhm.
They also probably don't really understand DNS. So adding DNSSEC on top of that doesn't make that any better for them.
yes, but for small companies, and we many times these are anecdotal examples. We sometimes observe these small companies just relying on the default name server managed by registrar. So that is why we're encouraging our registrars to support DNSSEC on their default name servers. If that's the case, then the small companies do not need to care about DNSSEC because they will automatically turn on the DNSSEC.
Sure.
Yep.
Thanks.
Okay, well, thank you again. Okay, so that's everything for this meeting. Thank you again to both the speakers. I think there was 2 really excellent talks. I think both TJ and Netta will be around for at least tomorrow, I think possibly most of the week. So if you're interested in the work, please grab them in the hallways. And thank you for your attention. And if you can pass the blue sheets to the front.